Hey everyone. So today we're going to be talking about how to write these equilibrium expressions just by looking at the balanced equation. It's not going to tell you the actual value. For that, you have to do a little bit of experimentation, but we can write out the expression. We can write out the ratio of these guys. Now, the way that we can do that is, remember, it's always going to be products over reactants. So it's going to be the products over the reactants, and it's going to be the concentrations raised to the power of their coefficients. So let's go through and kind of work through these four here. What is this going to look like? So for this first one, what is the equilibrium expression for this guy going to be? Like if you're looking for K or you're looking for Q, what is it going to be? So we know it's going to be a ratio. We know it's going to be products over reactants. Products over reactants. So what are the products? In this case, it's O2. So it's going to be the concentration of O2, 2, raised to its coefficient. Now this one's just 1, so it's raised to the power of 1. Then it's going to be multiplied by the concentration of NO2, raised to the power of its coefficient. It would be 1. And products over reactants. So we look at our reactants. Concentration of O3, raised to the power of its coefficient, 1. There's a 1 here. And we're going to multiply that by the concentration of nitrogen monoxide, NO, raised to the power of its coefficient, 1. And this is what we're going to use if the reaction's at equilibrium. Then this calculation here will get us K, our equilibrium constant. If it's not at equilibrium, we can still use this, but instead of getting K, we're going to be getting Q. We call this the reaction quotient. So that is how we can go through and actually come up with that formula, how we derive that formula. Okay, that was pretty simple because all the coefficients are 1, right? That's pretty straightforward. But let's go through and do B. All right, so I'm going to make this a little bit larger. So remember, it's always going to be the same thing, products over reactants. So we look at our products. We have CO2. And remember, it's the concentration of CO2, so like molarity, raised to the power of its coefficient, 2, squared. So it's going to be raised to the power of 2. The reactants are going to be CO and O2, carbon monoxide and oxygen. So it's the concentrations of these guys raised to the power of the coefficients. So oxygen is just 1, no big deal. And this one is 2. There we go. That's all we're going to do to write these equilibrium expressions. That's all we're really wanting to do right now is just write them. We'll add numbers to it later, but I just want you to be able to create these things. So, all right, now C. Let's try this one. At any point in the video, if you're wanting to give it a shot, pause it and then do it. See what it is. So feel free to pause now. All right. So remember, products over reactants raised to the power of their coefficients. So products into O. It's the concentration raised to the power of its coefficient, so just 1. And H2O raised to the concentration raised to its power of its coefficient, so it's going to be squared because the coefficient's 2. Okay, now this is not quite right. I'm going to get to why this isn't quite right later on. Well, again, we can talk about it right now. I'm going to ask you, can we have a concentration of a liquid? Not really, right? Liquids don't really have a concentration. So we in an equilibrium constant like this, if you see a liquid, you can ignore it. It just isn't there. We don't have a concentration for this guy, for a liquid. So we can get rid of it. On top of that, a solid. This guy is a solid. Can you have a concentration of a solid? No, you can't have a concentration of a solid. So we can ignore that as well. So the equilibrium expression for this guy is going to be the concentration of N2O. And there we go. Not a very impressive one, but yeah, there it is. Gases and aqueous things are the things that you can use equilibrium expressions for. All right, and for this one, we can use this one. This is H2O gas, so we can actually go through and use that. And hydrogen gas and oxygen gas. So, concentration of hydrogen, raised to the second power. Concentration of O2, raised to the second power. Oh, no, raised, there's no coefficient there. And then on bottom, concentration of H2O gas. We can do this because it's a gas. We can do that. Yeah, so gases, I'll talk about that in a moment. So yeah, this is how we go about writing equilibrium expressions. If you're watching this on Friday, then Thursday, or I should say Thursday night, before Friday, on Thursday, that's all we're doing today. Or Thursday was just writing equilibrium expressions, learning the rules for that. And now, once you have that equilibrium expression, you can go through and if you are given the concentrations, or if you can find the concentrations at equilibrium, we then can use your equilibrium expression, that formula ratio you made, to find K, to find the actual number for your equilibrium constant. Okay, so for this, let's go through and write our equilibrium expression. It's going to be concentration of nitrogen times the concentration of hydrogen gas, 2, over the concentration of ammonia. All right, and so now we can go through and replace these guys with their concentrations that at their equilibrium. So 8.5 times 10 to the negative first, and it's going to be these are all raised to their first power. Oh wait, no, this isn't balanced. I tricked myself. This isn't balanced. We need to go through and balance this first. So this is going to be 2, and this is going to be 3. So now everything is balanced. Now let's rewrite that equilibrium expression. It's still going to be nitrogen. That's still to the first power. But now we have hydrogen gas, and this is going to be raised to the third power. And ammonia gas is going to be raised to the second power. So now we can just plug things in. On the bottom, we're going to have 3.1 times 10 to the negative second, all raised to the second power. For nitrogen gas, 8.5 times 10 to the negative first, and hydrogen gas is going to be 3.1 times 10 to the negative third, and all of this is going to be raised to the third power. Okay, so now we can just pull out a calculator and go through and calculate this. Okay. So, I'm not used to this calculator, so I'm going to do this in steps. So 3.1 e to the negative second, and we are going to square this. All right, so if we did that, then we get 9 point. Just move you over here so I can see you. 9.61 times 10 to the negative fourth. All right, and the other thing is 3.1. 3.1 e to the negative third, and I am going to multiply this by exponent of 3. Okay, do that. Where are you? There we go. 3. Boop. And that turns into 2.97 times 10 to the negative 8th. Now we can multiply all of this together. Multiply 8.5 to the negative first, and divide that by 9.61 e to the negative fourth. And all of this turns out to be 2.63 times 10 to the negative fifth. With that in mind, we now know something about this guy, right? We know something about this equilibrium. This is an equilibrium that's less than 1. So since we know it's less than 1, what is going to be favored on this? Is the product's going to be favored or the reactant's going to be favored? Since we know this is less than 1, this ratio has to equal less than 1, which means that it is going to be favoring the bottom part of this ratio, favoring the reactants, the ammonia gas. So this is going to be the major component of our equilibrium. There's going to be a little bit of this and a lot of ammonia. That's going to be kind of what this equilibrium is going to look like. Okay. So we can do the same thing with gases. Now, instead of doing concentrations for gases, we can also use pressure. Basically, this is going to be the partial pressure of gases can be used in a very, very similar manner. It's the same idea, but instead of saying it's still products over reactants, it's still raised to their coefficients. All of it's the same. The only difference is instead of using molarity, we're going to be using atmospheres or PSI or whatever you want to use for that torr. You can use torr. Same idea. You would just do the same process. You would write your reaction expression, input your atmospheres, raise them to their coefficients, and then calculate. And this, instead of saying there's going to be lots of little subscripts here, kind of like the delta H had, delta H combustion, delta H of formation, delta H of reaction. In a similar way, you're going to have little subscripts for Ks. In general, you're going to say KEQ or KC for an equilibrium expression or equilibrium constant for a reaction, or one for using concentration. KC is concentration. KP means that it's a gas and you're using pressure. So this is just a way of letting us know that when we're talking about a KP, it's like, hey guys, we're using pressure to figure out this ratio. It all still works out, and if you really wanted to, you could convert KEQ to KP. It's not necessarily difficult. You can go through and figure out moles over volume, and and that equals P over RT. It's not going to be terribly difficult. You can use PV equals nRT to convert concentration, moles over volume, to pressure. The thing is, it's not going to be on the AP exam. It's not going to be tested. You don't need to know how to convert. The only thing is, I just want you to know the difference. If we're talking about KP, use pressures. If we're talking about KEQ or KC, use concentrations. That's the only difference there. All right. Next step is about manipulating lots of reactions together. We can do that. We're pros at that now. You guys know Hess's law. You're the masters of the flipping and the multiplying and the adding them together and the things. In elementary steps, same idea. Okay, but the rules for K's are a little different because we are like with the coefficients, we're raising them to a certain power. We're doing things a little different. So think about it. You have to think about what we're doing. If we go from like A to B, and we have A on the left-hand side, B on the right-hand side, so we would say products and reactants. If we flipped this reaction, we're flipping the products and the reactants. So in that case, we need to flip our equilibrium expression as well. Now, you can either go through and actually try to flip it, but if you already know K, what you can do, a shortcut here, is just to take the reciprocal of it. So for example, if we had some equation and we found out that K equals 2, all right? I don't need to go through and think about all the numbers here that made up and calculated to 2. I don't need to know. If I flip the reaction because of Hess's law or something like that, then I know what K is going to be. K is just going to be the reciprocal of 2. So it's going to be 1 over 2, or 0.5. That's all we're talking about. If you do that, if you flip the reaction, we're going to be taking the reciprocal of the K, the equilibrium constant. All right, now what happens if we multiply? If we're multiplying a reaction, so again, sometimes you need to have 2A going to 2B because of Hess's law or something like that. So we're going to be, if we do that, then what happens to K? So originally, if K was 2, what would this new K be? Well, instead of multiplying it like we did in Hess's law, we raise it to the power of whatever we're multiplying by. So if we double this, we're going to raise this to the power of 2. So 2 squared now, so that's going to turn into 4. Okay? And let's say we have a whole bunch of different reactions. If we have 3 or 4 reactions, and each of them have a different K. So this one has K equals 2. This is K equals 0.5. And the next one is K equals 30. Okay? Well, what do? If we can go through and we do our normal kind of cross out thing, and we add it up, and we get an overall reaction, what is the new K of this going to be? So instead of adding up things like in delta H's, we would add up the delta H's. Instead, we're going to multiply all of these together. So, pull back my calculator. 2 times 0.5 times 30. So, well, yeah, no, I guess that makes sense. 2 times 0.5 is going to be 1. So our new K is going to be 30. Let me choose some different numbers here. Let's not do 0.5. Let's do 0.03. There we go. So now what is this going to be? 2 times 0.03 times 30. And we get a new K of 1.8. So this is how, if we flip a reaction, we know we can flip K. If we multiply a reaction, we raise the K by whatever power we're multiplying by. And if we're adding the reactions together, we're multiplying the case together. That's going to be how we're going to be manipulating different reactions together. All right. So there's that. Oh, and here's the slide that tells me solids and liquids do not have concentrations. If you see a reaction, you completely ignore solids and liquids. You can just, they don't exist. So remember that they're there, but you don't have to think about them in terms of your calculations. Later on, I'm going to be talking about something called a rice table. Rice tables are going to be kind of the new way we're doing problems. You know, it seems like every time we have a new unit, there's a new way of thinking about math. So rice tables are going to be the equilibrium version of math. I'm going to go into that after spring break, so I'm going to give you guys a bit of a reprieve. All right, so I will see you guys later. Thanks for watching the video.